All right, so we're going to do some really simple proofs using this, using these axioms and theorems. But because these axioms are so wide-reaching, that there's so many different types of axioms, I'm not going to state them explicitly. If this was a really serious, hardcore proof writing class, then we would be really explicit about which axioms we were using. We wouldn't use anything that wasn't an axiom or that we hadn't deduced by axioms, deduced from axioms ourselves by hand, but this is going to be a little bit lighter than that. So I just want you to be aware of these things. If you go on and do more rigorous proof writing, you'll learn about that. But we're really just kind of trying to, if proofs are cars, we're just trying to drive the car. We're not trying to, mill our own cylinders for our supercharged engine or something like that. Okay, so what I want to do is I want to give us some sort of toy definitions. So these are definitions that we can use to prove some things. And these are going to be even, odd, and rational. So we say an integer is even if there exists, an integer n. I didn't tell you what the name of the integer was. That's a problem. An integer n is even, so I'm defining even, if there exists an integer k such that n equals 2k. Now some of you are saying, oh no, that's okay, Steve, I'm really smart, I already know what an even number is. That's cool. We're going to use this definition, okay? And you say, well, no, dude, I know what an even number is. It's like if you had an even number, then you could divide it by 2 evenly. Like, yeah, good. We're going to use this definition. Okay, so, all right, a little weird, but I'm going to insist that we use this definition. Moving on, an integer is odd if it is not even. Okay. So that's fine. I'm gonna prove us a little result here. I'm gonna state a little result without proof, and say we can equivalently characterize odd numbers by saying that an integer n is odd if there exists an integer k such that n equals 2k plus 1. So I'm going to take these as equivalent definitions. I haven't actually proved this, but I'm going to use these as axioms. We could prove one from the other, but I'm going to go on ahead real quick and not. The last definition I want, which is going to seem maybe even a little bit further out, like why are we talking about this? But this is another important definition. So a real number is called rational if it can be written as P over Q in lowest terms for integers P and Q with Q not equal to 0. So what do I mean by lowest terms? I mean I can't cancel the same factor from the top and bottom. So is 2/4 a rational number? It is a rational number because I can write it as 1/2. All right. We're going to see more stuff about rational numbers as we move forward here. All right. So first we're going to do a direct proof. So a direct proof follows a straight line of implications. Now, this is kind of a crummy definition because every proof is in some sense a direct proof because we read from left to right one line at a time. So already we're seeing like these quote unquote types of proofs. These are rough ideas. So an axiom, that's not a rough idea. That is a statement, we've defined statement, that is generally accepted to be true. So what does generally accepted mean? It means that when we have a conversation, we say, what are the axioms? What are the things that we accept to be true? Okay? That's not a fuzzy definition. This is a fuzzy definition, and that's because the edges are fuzzy. Some proofs, two people can look at it, and one would say, oh, that's a direct proof, and some people would say, it's not quite direct. That's kind of an indirect proof. Don't worry about it. We're just going to say direct proof is a flavor, it's a type, and we're gonna see more about what is direct versus what is less direct. So we're going to do an example. So show, if I say show, I mean prove. Show that if n is even, then n squared is even. Okay? Proof. Now you might say, oh, well, yeah, like 4 is an even number and 4 squared is 16. Therefore, yeah, so that's just how it works. That's not a proof, that's an example. So you can give me an example and then maybe use that to illustrate your proof, but that's not the same as writing a proof. So here's a proof of this fact. Since n is even, what does it mean to be even? Since n is even, that means there exists an integer k such that n equals 2k. Since n is even, there exists an integer k such that n equals 2k. All right, cool. Now, we're going to consider the quantity n squared. Now, I'm going to use this phrase a lot. So I want you to imagine that you're at the coolest party that you've ever been to, just like whatever kind of party you like. I don't know. But you know that your party is really just the best party ever if while you're at that party, you hear over all the noise or the music or the shouting or whatever, you hear someone adjust their monocle and say, consider the quantity, right? That's, oh man, that must be such a cool party, right? Like that would be, I would know that I had really made it in life if someone said out loud at a party, consider the quantity. I'm just waiting for that. Anyways, so, here's the person. They've definitely got a monocle. How is there like a chain or something? They're very smart. I was going to draw a light bulb, then I felt like I probably couldn't manage a light bulb. Now I feel like I can't step away from the challenge. Oh gosh, this is a garbage light bulb if I've ever seen one. We're going to pretend a light bulb never happened. Luckily, this isn't going to be recorded or posted on YouTube. Wait a minute. Okay, so we're going to consider the quantity n squared. So what does that mean? I write n squared equals, and then I'm going to write n in terms of some other quantities. So I'm going to, in place of n, I'm going to write 2k. So n is 2k. So n squared is 2k quantity squared. And this is, I'm just going to multiply this out. This is 4 k squared. And I can factor a 2 out. Why would I factor a 2 out? Just because. I'm going to factor 2 out and get this as 2 times 2k squared. Now, I said explicitly we're not going to list off all of our axioms, but one of the axioms of the integers is that if you multiply two integers together, you get an integer, which means that I have 2 times an integer here. 2 times an integer. Now this is called closure, and I could say, by the closure of the integers, we now have 2 times an integer, that's fine. You can do that if you want. But basically, once you get here and you say, we notice this is 2 times an integer, I'm going to say, okay, good. That meets the definition of even, therefore n squared is even. And we are done. And when we finish a proof, we draw a little box and color it in. That's our reward for finishing the proof. So this is what we call a direct proof, because we kind of had an if-then structure. We kind of said if n is even, then n squared is even. So what we did was we started with the first thing. We started with this, and then this implies something, and this implies something, and that implies something, and that eventually implies this. Okay, so this is kind of a direct proof. Now some people might say, well, this isn't very direct because, you started with n is even, and then you took this side step to considering n squared. Okay, fine. Some people might say that's not direct. I would say this is a fairly direct proof. Okay? If the distinction's not clear, don't worry about it too much yet, because now I want you to see something that is highly indirect that you can compare with this. So example, show that if n squared is even and n is an integer, then n is even. Now, I want to point out something minor here. Here, I just said suppose n is even, and by supposing n was even, we knew it was an integer. But now I'm saying suppose n squared is even. I don't necessarily know that n is an integer, right? What if n squared is, say, 6? Well, the square root of 6 is not an integer. So this is only going to hold when we have that n squared is a perfect square, or that n is an integer. So if n squared is even, and n is an integer, then we get n must have been even all along. Okay? Proof. Now, if you try to regurgitate this proof for this statement, you're going to have a bad time. Okay? That's just not going to go well for you. I believe that there probably is a more direct proof out there, but what we're going to do instead is we're going to do a proof by contraposition. So I'm going to take this whole thing and set it equal to P, and I'm going to take this whole thing and set it equal to Q. Now I claim that not Q implies not P, and this is again the contrapositive. So I claim that not Q implies not P. So now let's prove that not Q implies not P. So what is not Q? Well, not Q would be, it is not the case that n is even. But that's the same as saying n is odd. And if n is odd, that means there exists, see how handy it is to have these symbols? There exists an integer k such that, see how handy these symbols are? N equals 2k plus 1. Right, this was our definition of odd. One of our two definitions of odd. So n is odd if there exists an integer k such that n equals 2k plus 1. Right? And that was because it is not the case that n is even meant that n was odd. Right? We also had, this was another characterization. We said an integer is odd if it is not even. So again, there's a little bit of dust being swept under the rug here, but hopefully not enough to make anyone super uncomfortable. So not Q means there exists an integer k such that n equals 2k plus 1. Now remember, we're at the party. There's the din of laughter and people having a good time, and then of course we're at the precipice of discovering this is one of the coolest parties we've ever been to when we hear someone say the magic phrase, consider the quantity. There it is. Oh, it feels so good. Consider the quantity n squared. Okay, we're not always going to consider the quantity n squared, but in these two examples, we find out something about n and we try to prove something about n squared. All right, so we consider the quantity n squared. Well, in this example, n is 2k plus 1, not just 2k. So n squared becomes 2k plus 1 quantity squared, which is, of course, 4k squared plus 4k plus 1. All right, now I just squared a binomial, and I went a little bit quickly. If that was too fast for you, pause the video and work it out, okay? If that wasn't too fast for you, great, we're still going. But if that was too fast for you, pause the video and work this out. This should not be 4k squared plus 1. It's 4k squared plus 4k plus 1. Now I can factor out a 2 from some of this, and I'll get 2 times the quantity 2k squared plus 2k, and then I'm going to add on a 1 at the end. All right, again, if that was too fast for you, pause the video, check that this equals this. All right? Now, this is an integer. So guess what? We just showed, so you're going to see me do this double arrow. This is an implication on the higher order. So this is an implication meaning this statement implies this statement, as opposed to here where the implication is the statement. All right? If that's not entirely clear, that's okay. Just wait. You'll start to sense when I'm saying this is in place of me saying therefore in English. Okay? So therefore, n squared is 2 times an integer plus 1, which means n squared is odd. N squared is odd, okay, but guess what? N squared is odd. Well, I just wrote n squared is odd. That means n squared isn't even. Now, keep in mind that we started with this n is odd thing, so we got from n is odd to n squared isn't even, and we were trying to prove something about n being even, so we're sort of backwards, and we're doing something backwards. But if n squared isn't even, what's that mean? N squared isn't even is precisely not p. Okay? Now, I guess it's not precisely not p, because this should have been p, and we're just talking about integers n. But what I've shown is that not q implies not p. All right? Not q implies not p. But remember, not q implies not p. That is logically equivalent to p implies q, which is what we were trying to prove in the first place. So I have finished my proof by contraposition. Now, if you thought this first proof up here seemed indirect, if you thought this proof seemed indirect, hopefully you see now that this is a lot more direct than this. All right, here I had a task. I said I start here and I end here. Start with n is even, end with n squared is even. But here we start with n squared is even, we try to end with n is even, but that was kind of too hard to do. So instead we inverted everything and flipped it backwards. That is, we negated p and q and then tried to prove not q implies not p. We had to analyze what is not q and then do some direct reasoning. And then we realized that the output of our direct reasoning was not p, which means that we had not q implies not p. But not q implies not p is the contrapositive of the original implication, which means not q implies not p is logically equivalent to p implies q, which is what we're trying to prove in the first place. If that's a little rough, if that's a little bit much, that's okay. You can pause the video and watch it again. Also, as always, feel free to email me questions. Now, if that felt rough, I just want to warn you, that's a warm-up for what comes next. And what comes next is one of the hardest proofs that we'll probably cover this semester. So it's kind of a good thing that we'll be seeing it early. Anyways, and this is called a proof by contraposition. You notice that I said I'm using the contrapositive here, but I guess I should say this is a proof by contraposition. Okay, I didn't really define proof by contrapositive or proof by contraposition, but it's a proof where you use the contrapositive. All right, I think